Okay, when I have equilibrium, remember that's delta G equals 0. And the book comes up with an equation relating delta G at non-standard conditions to standard delta G, and the reaction looks like this. If you're interested in the derivation, I'd suggest walking through the book. You don't need to know it, you just need to know it does occur and be able to work with this reaction. So, for a given reaction, at a particular set of conditions, the change in free energy is equal to the standard change in free energy, that's delta G0, plus RT ln Q. R is the gas constant, our buddy 8.31, and it's in joules. T is temperature in Kelvin, and ln, guess what? Natural log, and Q. Q is the reaction quotient. So there's our equation. Remember, at equilibrium, Q equals K. So now I can substitute in for that, and I get at equilibrium, delta G equals 0, which equals delta G0 plus RT, and now I'm going to use natural log of K, because K is my equilibrium constant, which is Kc or Ka or Kb. All those lovely equilibrium constants we've been working with for the last few chapters. So that simplifies down into delta G0, so the change in free energy at standard conditions equals negative RT ln K. So this is a direct link between the amount of free energy in a reaction and the equilibrium constant. So let's take a look at what happens to delta G when I change K, or to K when I change delta G. So if delta G equals 0, we're at equilibrium. K is equal to 1 because the reactants and the products are balanced. Delta G is less than 0, we have a spontaneous reaction. So our reaction is being driven towards products. K is going to be greater than 1. If delta G is greater than 1, we have a positive delta G, non-spontaneous reaction. So that means K is less than 1. We have mostly reactants. Hopefully that makes sense. So let's take a look at another example. Okay, here we have the reaction of iron corroding or rusting. So we have iron plus oxygen gives me 2 iron 3 oxides, Fe2O3. And I'm supposed to calculate delta H, delta S, delta G, and then find K. So I'm going to do one step at a time. From the back of the book, I can find the heat of formation for my 3 substances, so I can find delta H. And that's equal to 2 times the heat of formation of iron oxide, so that's minus 826, minus 4 times the heat of formation of iron, well that's 0, plus 3 times the heat of formation of oxygen, well that's 0. So delta H for my reaction is 2 times 826 kilojoules per mole, but I want to put that into joules. So I'm going to get negative 1.65 times 10 to the 6 joules. I'm going to do the same thing for delta S, and it's going to be the entropy of the products. So the entropy of my products is 90 times 2 minus entropy of formation. Entropy of formation of elements is usually not 0 because there's some randomness to how I put them together. So for iron, it's 27. So 4 times 27 joules plus 3 times for oxygen, it's 205. If you stop to think about it, hopefully you'll realize that the entropy of a gas is generally higher than the entropy of a solid because they're moving and they can be in large number of positions relative to each other compared to solid. So I do the math for delta S and I end up with negative 543 joules per Kelvin. And the moles, remember, drop out because I'm multiplying by the coefficients, which are number of moles. Okay, one thing that didn't get included here is we're at 25 degrees Celsius, so that's standard temperature. So now I can find delta G. So for delta G0, I have delta H, that's negative 1.65 times 10 to the positive 6 minus temperature. 25C is 298 Kelvin times, and my delta S is minus 543. So I find a delta G0 of negative 1.49 times 10 to the 6 joules. Okay, that takes care of finding delta H, delta S, and delta G. Now I have to find K. From before, delta G0 equals negative RT ln K. So delta G is negative 1.49 times 10 to the 6. That equals R is 8.31, T is 298 ln K. Doing the algebra on both sides, got negative 1.49 times 10 to the negative 6 divided by negative 8.31 times 298. I get a positive 601 equals ln K. Well, easy way to do that is just to say K equals e to the positive 601. And then I'm done. And there's my equilibrium constant. So is this reaction spontaneous? Yes. delta G is negative. Does this reaction favor reactants or products? Well, if I look at the K value, it most definitely favors products. This is my tie between the past 3 chapters and Chapter 6, Thermodynamics. We're continuing to link these things together. This essentially takes us through Chapter 16.